Hello everybody, thank you for joining me in another recording, this time still on integration. We're getting quite deep into chapter 11 now of the year 13 content, the 10th video in integration, which is, as I've said, the largest chapter. So today we're going to have a look at a technique known as separating the variables to perform integration for an equation. This is often a topic which confuses students, so I've embedded a couple more worked examples than what I normally maybe would do, but before that, almost as ever, there are some warm-up questions to attempt, so I'll reveal them to you. So here they are. Arithmetic sequences, so you need to know about your laws of logs and natural logs. Question 2, a bit of mechanics for you thrown in, and question 3, again some natural logs, and I'll let you figure out what to do with the rest. So I'd suggest to pause the video here, attempt these questions, check your solutions by then skipping ahead to see them, and hopefully yours will match mine. But if not, hopefully the solutions should help you to make sense of things. Okay, assuming you've attempted those warm-up questions, let's have a look and see how to do them. So question 1, we have here an arithmetic sequence. Going back to basics, this just means that the gaps in between the terms are constant. So we need to find the exact value of the constant k. So like I say, the gaps in between an arithmetic sequence are constant. So if I just ring one in blue, one in green, and one in red, then what we can say here is the difference between the last and the middle has to be the same as the difference in between the middle and the first. So in other words, because it's an arithmetic sequence, we can deduce here that ln of 3k plus 5 minus ln of 3k plus 1 must be one and the same as ln of 3k minus 1. So ln 3k, yes, minus 1. I've miscopied. Apologies. I'll just correct that now very quickly. That should be a minus, my bad. So it's this ln 3k minus 1 subtract ln 3. After doing that, we now need to remember laws of logs. All the logs are to the same base e, for all natural logs. Ln of one thing minus ln of the other, if they're to the same base, we can combine this into one single log. It's going to be ln of the first term, we're taking the natural log of, divided by the second one, because it's minusing. That'll have to equal on the other side ln of 3k minus 1 all over ln of 3. Sorry, just 3, I mean to say. Not doing very well so far today. Hopefully I'll get warmed up. So let's just have a look and see what we have here. So we've got an equation, one side equals the other. Both are natural logs, so natural log of this thing equals natural log of the other. That can only be if what we're taking the log of on both sides are equal. So in other words, what we can do here is deduce that 3k plus 5 divided by 3k minus 1 equals on the other side 3k minus 1 all over 3, because that has to equal that for it to work, essentially. So now we've got one fraction equals another. I tend to solve these by just cross multiplication. So this denominator multiplied by that numerator will equal this denominator multiplied by that numerator. So from there, we can proceed and say that 3k minus 1 squared must equal 3 lots of 3k plus 5. If we expand this out, what we'll next have, give myself a bit more space, expand this out, I'm going to get 3 to the power of 2k, then take the product and double, so it's going to be minus 2 lots of 3 to the k. Minus 1 all squared, of course, is positive 1. That needs to equal 3 lots of 3k plus 3 times 5, which of course is 15. We can now rearrange this to get one side equal to 0. So if I subtract everything away from this side on the right to make it equal to 0, I'll now get 3 to the power of 2k minus 2 lots of 3k minus this lot here gives us minus 5 lots of 3k. positive 1 minus 15 gives minus 14, and that'll equal 0. At this point, it's possibly, potentially confusing what we're going to do here. What I would say to students is if we have some equation here and we notice we've got powers and the base is the same, if one power is double the other, this essentially is going to be a hidden quadratic. So what we're going to suggest to do here is let big X equal 3 to the power k. So make a substitution, let X equal 3 to the k. And if we do that, this will transform this into a more nicer looking form, dare I say. So 3 to the 2k is the same as 3 to the power k all squared. In other words, that's going to be x squared. This becomes minus 5 lots of x minus 14 equals 0. This will now factorise, and in fairness at this stage, if you really wanted to, you can just use your calculator, but doing it purely algebraically, the two values that multiply to minus 14 sum to minus 5 are going to be positive 2 and minus 7. So from here, one bracket's got to be equal to 0, clearly. So either big X is going to be minus 2, or big X is going to be positive 7. What was big X? Well, it was 3 to the power k. So in other words, 3 to the power k is minus 2, or 3 to the k is positive 7. 3, of course, is a positive value. We can't ever arrive at a negative value for that. As well as that, if you were to try putting something in where 3 to the power k is a minus, that'd give us minus 2 minus 1. We can't take natural logs of that. So either way you consider it, this here is not a valid root. We need to reject that one, because that would just break if we put it in. So we've got to have 3k equals 7. So from that, if we take natural logs of both sides, we get ln of 3k equals ln of 7. The k can come to the front using the laws of logs, so k lots of ln 3 equals natural log of 7. Therefore, the final step we have is k has to be ln of 7 divided by the natural log of 3. And that is our final answer. So, not the easiest of warm-up questions, but you know what? Sometimes the A-level exams themselves aren't easy either. So, there's number 1. Let's have a look at warm-up question 2. Warm-up 2, some mechanics for us. So we've got an arrow which is fired from a horizontal ground with an initial velocity of 100 meters per second. I don't think that an arrow would actually go that fast. Probably should have called it a bullet. Anyway, never mind. Angle of 30 degrees above the horizontal. We're going to model the arrow as a particle and work out the time taken, first of all, for the arrow to hit the ground. So what I want to do firstly is just to actually do a tiny sketch of this situation. So we've got the arrow as a particle, so there's my blob of an arrow. It's fired up at an angle of 30 degrees from the horizontal, so I'm going to draw this in. That's 100 meters per second initial speed. And as well, this will be useful later. We need to consider at some point the components. So horizontal component of velocity and a vertical component of velocity. The angle, of course, is 30 degrees, so I'm going to label this one in. And the horizontal component is going to be 100 cos 30 initially. Now, if you want to check on the exact trig ratios, cos 30 is one of these exact ones. So if you want to just check this, 100 cos 30, it's going to give us 50 root 3. Whereas the vertical component of motion is 100 sine 30. And again, if you want to check that one, sine 30 is actually a half. So upwards, that's 50. The time taken for the arrow to hit the ground. Well, going down on the arrow is a force, which is a force of gravity. So obviously, there's going to be an acceleration going downwards of 9.8. So if I add this on here, acceleration downwards due to g 9.8 meters per second squared. This is actually a constant acceleration question. However, all we need to do now is consider either horizontal or vertical. If we're considering the time taken for it at the ground, what we're wanting here is to consider vertical motion only. When it hits the ground again, because it starts off from horizontal ground, its vertical displacement will again be 0. So let's just consider vertical motion only, or vertical components. And here, I'm going to take up as positive. So considering the vertical motion only, with up being positive, let's just think about what we have in terms of suvat. Constant acceleration means suvat. When it hits the ground again, its vertical displacement will be 0, because it's not moved away vertically. It's gone up, then come back down again. U, the initial speed in terms of vertically, is positive 100 sine 30. The acceleration due to gravity, I don't know its final velocity, but I do know the acceleration will be minus 9.8, because that's acceleration due to gravity. The time taken I've not asked for. I know what we asked for it rather. Time taken, so I'm going to put a question mark there. The final speed, I don't know, don't want to know yet. So I'm wanting an equation of motion which does not involve v. So again, seems to be a most common one, this one. We can use s equals ut plus a half at squared, filling in what we know to arrive at our solution for t. So we've got 0, because s is 0. Initial speed, u is 50, like we said, because 100 sine 30 is 50. So that's 50 t plus a half times minus 9.8 times t squared. Just highlight what we've used there. We've used u is 50, which is the same as 100 sine 30, and a is minus 9.8. So what we've got here is a quadratic equation. So essentially, 0 is 50t minus 4.9t squared. So if you use the quad formula, or the calculator, or whichever method you want to use to solve a quadratic, we can do this now. So I'm going to use the calculator to be fair. Let's just type it in. So if I go to, on this one, menu, I'm going to scroll to option A for equation, press equals. We want a polynomial, so I'm going to press option 2, and the degree, of course, is 2. So my x squared term, the quadratic term, is minus 4.9. Over here, the t term, standard x term, is 50. And I've got no constant, it's just 0. So we've got t is 50 over 49. Or with one, t is 0. Now t is 0, that relates to its starting point, because it starts on the ground. So again, its vertical displacement is going to be 0 when t is 0. That's the trivial solution. So we want x1, this solution, 500 over 49, which as a decimal, we can say is 10.2 seconds. So t equals 10.2 seconds. That's part A done. We can now consider part B. So in part B, we're asked to find the maximum height of the arrow. Now, we could either do this using symmetry. If its time is 0 when it starts, 10.2 when it hits the ground again, the maximum height will be when the time is half of this total flight time. You can sub in t as 5.1 into s equals ut plus a half at squared. That's one way of doing it. I'll leave that to you to experiment with if you'd like. Another way we could do it is again to just use suvat. So again, vertical motion only. So this is vertical motion. I'll just make a note to say. This is all vertical. So the maximum height of the arrow, that's what I want to find. I want to find its maximum vertical displacement. So I'm going to put a question mark there because I want to find that. The initial upward speed, of course, is 50. Now, the vertical speed, when it's at its maximum height, instantaneously, its vertical speed is going to be 0. It's not going up vertically at the time when it's at the maximum, but it's not quite dropping down either. So we set the vertical speed to be 0. A is still 9.8. This time we don't know t. We don't care about t. Well, actually, I did sort of say, actually, we could work out that t is 5.1 using the symmetry of it. That's approach 1. I'm just showing you approach 2 here. So what Suvat formula can I use which does not involve t? So let's just think of that one for a second. I think the one we need to go for is v squared equals u squared plus 2as. So if we use that one, v squared, which is going to be 0 squared, which is 0. That's going to be u squared, which is 50 squared, plus 2 times minus 9.8 s. So if we just move ahead and simplify this, we've got 0 is going to be 2,500 minus, well, 2 times minus 9.8, that's minus 9.6 times s. So therefore, hopefully you can see that s is going to be 2,500 divided by 19.6. Bust out the calculator. 2,500 divided by 9.6, press SROD. That gives us a height of 127.6 meters to 1 decimal place, 127.6 meters. And the last part to this question, we're asked to find the speed of the arrow after 3 seconds. So let's just think about this in terms of the actual particle. So after 3 seconds, the vertical component of motion is what we really need to find, but horizontal velocity is going to be kept the same because we're not including any air resistance in our model. So the particle is not going to accelerate in the horizontal direction. So VH, the horizontal component, would still be 50 root 3. To find the vertical component of velocity, what we can do here is we can use v equals u plus at. So if I just that's one we're using for here. So the vertical component of velocity will be the initial component of the vertical velocity plus the vertical acceleration multiplied by the time. So in other words, v, subscript v, the initial upward speed, of course, we know is 50. A is a minus 9.8. So this becomes minus 9.8 multiplied by t, which of course is 3. And that gives us a value of, let's just work this one out, I think it's 20.6, but I'm just going to double check. 20 minus 3 times 9.8. Yeah, 20.6. So putting these pieces together, horizontally we've got that, vertically we have that. So essentially the speed of the arrow is essentially the magnitude of its velocity at that point. So I'm trying to find this here, the magnitude of its velocity. It'll still be going up. And then in terms of components, we work these out. So going along, the vertical component, so the horizontal component was 50 root 3. Going along, that's the horizontal. And vertically was 20.6. So just piecing these two bits together, we have that. So now, hopefully you'll see it's just a case of Pythagoras, to be honest. So now, V is just going to be 20.6 squared plus 50 root 3 squared, all square rooted. So we can do this using the calculator. So 20.6 squared plus 50 root 3 all squared. Let's see what this gives us. So root 20.6 squared plus 50 root 3 in exact form, all squared. Press equals. We get a value of 89.0 meters per second. And that's warm-up question 2 complete. Finally, for the warm-ups, warm-up question 3. I have a function f defined as a fraction here, algebraic fraction, minus ln of x plus 4. X is any real number. X has to be greater than some unknown as yet constant k. We have to find the smallest possible value of k. So don't overthink it. Let's just have a look and be thinking, why, if anything, what does there need to be a restriction on x? Over here, of course, we can put any x into the top of this. What value here would maybe make it explode? The key value here is -4. But again, there's a second clue in this question. If I put -4 here, I can't take ln of 0. I can't take a log of to any base of 0 or a negative. So it absolutely must be the case that x has to be larger than -4. So for that reason, k-min is the smallest possible value of k, rather, is going to be -4. In other words, k has to be bigger than -4 at the least. If I want k to be any smaller, that wouldn't be a sufficient restriction. For example, if I went for k-min being -5, that would allow k to be -4.5, which would still break f of x. So that's my absolute minimum value of k. Part B, f dashed of x. So already we should be thinking, okay, this needs to be differentiated. So what I'm going to do here, because this part here is a fraction, we're going to use the quotient rule. So if I just take this, what I'm going to do, because I think it's easy enough to do, I'm going to expand the numerator. So if I just say f of x equals, expanding this out, we get x squared. I'm going to get plus 6x plus 5 all over x plus 4 minus ln of x plus 4. So for B, f dashed of x, to differentiate the fraction, we need to use the quotient rule. So I'm going to differentiate the top, hold the denominator. So this is going to become 2x plus 6 x plus 4. Then I subtract away from that the derivative of the denominator multiplied by the numerator. So derivative of x plus 4 is just 1. Leave the numerator as is. It goes to x squared plus 6x plus 5. All over, this time, v squared. I'm running out of space again. I don't know why I do this to myself. So all of that is going to be over v squared, which is x plus 4 all squared. And then if I differentiate the natural log, differentiate ln of x will be 1 over x. You can use the reverse chain rule if you really want to, but differentiating ln of x plus 4 just gives 1 over x plus 4. So obviously this just needs to be neatened up and expanded. So first of all, if I multiply this all out, what I'll get here is 2x squared. 2x times 4, that's going to be 8x plus another 6x, so plus 14x. 6 times 4 is 24. So I've got this, and I'm going to minus off just x squared minus 6x plus 5, because if I expand that by 1, it's just going to stay as itself, isn't it? So I'm going to minus off all of that. So minus an x squared minus a 6x and minus 5. All over x plus 4 all squared, which we need to leave as it is, so I'm going to leave it like that. Now, because I want it as a single fraction, what I need to do is to get a common denominator. So what I'm going to suggest we do here is, for this one, I'm going to multiply top and bottom by x plus 4. If I do that, the denominator will become x plus 4 squared, which is exactly what I'm wanting. So then I'm going to take away x plus 4 all over x plus 4 squared. So if I take this and simplify it, 2x squared minus x squared, that's just going to give just 1x squared. So I'm going to have x squared 14x, this time I've got here minus 6x, that will leave me as just 8x, but again I'm taking away an x here, so 14x minus 6x is minus another x, will leave just 7x, and then just purely the constants, I've got 24, then I'm going to minus 5, 24 minus 5, that's 19, minus another 4, that gives 15. So I've got x squared plus 7x plus 15 all over x plus 4 squared. And that's the final answer for this one. Part C, I have to show that f is an increasing function. Well, increasing means the gradient is always positive. It's always going upwards. So I've got f dashed of x. So f dashed of x, just consider that. So consider f dashed of x. So x plus 4 squared is always going to be 0, considering this restriction upon x which we've placed. And then the numerator, x squared plus 7x plus 15, I can complete the square on this. That's going to give me x plus 7 over 2 all squared minus 49 over 4 when I complete the square plus 15. And that's going to be x plus 7 over 2 all squared minus 49 over 4 plus 15. Let's just work that one out. (11 over 4). Positive 11 over 4. And of course that's greater than 0. Just to make sure I don't run into part B. So because of this, and because of that, we've shown, because the numerator is positive for all values of x, and the denominator, this, is positive for all values of x, then f dashed of x is positive all the time. So therefore, f dashed of x greater than 0, so fx is an increasing function. And that's all we need to say for that one. So now we've done that, we can get on to the main bit of the lesson, which is going to talk about separation of variables. So let's have a look at the main part to this. Solving differential equations by separating the variables. Even the name seems confusing. A differential equation, but this is in the chapter of integration. So what's going on? So integration can be used to solve differential equations. In this course, we will only focus on using integration to solve first-order differential equations. For example, an equation involving dy by dx, rather than, say, a second derivative, which would be d squared y over dx squared. We can take second derivatives, but integrating from a second derivative, that more lies in the scope of further maths. The process that transforms such differential equations into equations which can then be integrated, that's known as separating the variables. So what does that mean? Well, first of all, it might be that you've got dy by dx, d theta by dt, or whatever. These are separated by treating the derivative notation as a fraction. It's not really, but in this case we treat it as one. So what we do essentially is we can multiply by dx or dt, or by whatever on this denominator, to get stuff to do with dy on one side of your equation and stuff to do with dx on the other. Then we need to rearrange the differential equation so that anything to do with x is on one side with dx and everything to do with y sits together with dy. If you're talking about d thetas, anything to do with theta is on the same side as d theta. Anything to do with dt is on the same side as dt. Afterwards, we then integrate both sides of the equation with respect to x and y respectively, or in terms of theta and t, whatever variables are happening or relating in the question. Secondly, if a coordinate pair is not known for the differential equation, we can only find the general solution of that equation, which will involve, of course, the plus c constant of integration. Or, if we actually know a coordinate pair, this is sometimes called a boundary condition, and we can substitute that in to find the particular solution to the differential equation. So let's have a look at a very, very simple introductory example, which just hopefully illustrates the concept. So worked example 1, which is purely introductory. By separating the variables, find the general solution to this differential equation, dy by dx equals 4. I know you know the answer to this, but just let's stick with the concept. Part B, we're then going to find the particular solution to that, given further that y is 11 when x equals 2. So, obviously, let's just do this as I'm intending. So, for part A, dy by dx is 4. Now, if we separate the variables, essentially I want to get the dx on another side, so I'm going to multiply both sides by dx. When you separate the variables, what it means is anything that looks like a derivative has to disappear. The denominator needs to become not the denominator, so dx at the bottom is never good. So then we're going to get dy on one side equals 4 dx. Then we integrate both sides. So I've only got one lot of dy there. If it helps you, consider like a ghostly 1. So one lot of dy equals 4 lots of dx. So integrating 1 with respect to y just gives y. Integrating 4 with respect to x, of course, gives 4. So I've got 4x plus the constant of integration. However, what we do know is y has to be 11 when x is 2. So I'm going to sub y is 11. These are the boundary conditions. And I know at that point x needs to be 2. So I'm going to plug in the value of 2 for x, because I know x has to equal 2 at that point. Whoops. So, obviously, 4 times 2 is 8, so 11 equals 8 plus c. Therefore, c is 3. Hence, the solution, the particular solution, is y equals 4x plus 3, which I knew you knew, but hopefully this illustrates the actual process of separating the variables. So x needs to move to the other side. I've got y stuff over here, nothing to do with y there. Nothing to do, all x stuff here, nothing to do with x over there. Then integrate both sides, solve. So that is as simple as it could ever get. You're never going to get anything that simple in the actual A-level exam. That's just an illustrative example to do the main ones. So now hopefully we've got the idea what we're doing. Let's have a look at a proper meaty one, if you like, worked example number 2. So worked example 2. We need to find a general solution to this differential equation, 1 plus x squared lots of dy by dx equals x tan y. So like I said earlier, we need to have all the x stuff together on one side, all the y stuff together on the other. So already you can see there's a mixture of x's and y's here, a mixture of x's and y's over there. The first thing, like I said earlier, the denominator part of the derivative has no place being a denominator if you're trying to solve a differential equation. So the first thing we're going to do is to multiply both sides by dx. So the next step, I have 1 plus x squared lots of dy equals x tan y dx. I still have y stuff on this side, so I want to just have x over here. And on this side, I want to have just y stuff, because I'm integrating with respect to y. So I need to get rid of the 1 plus x squared on this side. You could do 2 steps in one. I'm just going to do 1 step at a time. So I need the x squared stuff to live there, so I'm going to divide both sides here by 1 plus x squared. That will now give me dy. Over here, I've got x tan y dx all over 1 plus x squared. Again, though, I've still got a mixture of y's here. I don't want y on that side. I want anything to do with y together with the dy. So now I'm going to divide both sides by tan of y. That then gives me 1 over tan y with respect to y. I'll just be x over 1 plus x squared dx. At this stage, everything to do with y is together. Anything to do with x, again, is together over here. I can now integrate both sides with respect to y on this side, with respect to x on the other. So 1 over tan, I'm going to just replace this. 1 over tan is the same as cot. So the integral of cot y with respect to y equals the integral on this side. Now the x, I'm going to want to rewrite as 2x. So I'm going to put a half on the outside of this integral and then rewrite the numerator as 2x. A half times 2x is 1x, so it's equivalent. Why I'm doing this, I'll explain. If I rewrite the integral like that, essentially, the numerator now is the exact derivative of the denominator. If I differentiate 1 plus x squared, I get 2x. And that's a standard result if we're integrating. If we're trying to integrate something where the numerator is the derivative of the denominator, the integral is just the natural log of the denominator. So this will become half ln of 1 plus x squared. All we need to do now is to remember how to integrate cot y. Or we need to check the formula book. So I would always go to the formula book first if you're not sure. Cot y does actually integrate to the natural log ln of sine. So the next step, integrating cot y with respect to y, that's the same as ln mod sine y. And on this side, like I just said, that'll integrate to the natural log of the mod of the denominator, which I'm going to call plus c. I want to have a general solution, of course, to this. So what I'm going to do here, I'm going to just rewrite c as half ln of k. Now, if I just say k as a constant, ln of a constant is again a constant times a half is still a constant. So if I just rewrite plus c in this form, it actually allows me to combine this log and that log into the same thing. So then, ln of mod of sine y, that's going to be one and the same of a half ln. You can factorise out of a half ln because both are half ln's. So I've got ln of one thing plus ln of the other. We need to remember laws of logs. That can be combined into a single log where it's one thing multiplied by the other. So that's now ln mod of k multiplied by 1 plus x squared. Like so. Now because it's a half, this can actually be put back as a power here. So ln mod sine y is the same as ln of mod of all of that to the power of 1/2. However, to the power of 1/2, hopefully remember that's the same as a square root. So now we have ln of one thing equals ln mod of the other. That can only be true if ln of sine y, if sine y itself is exactly the same as root k 1 plus x squared. So therefore we can finish off. We have our general solution. So therefore sine of y equals k root 1 plus x squared. Let's now have a look at another worked example number 3. This one, we have a boundary condition this time. So given that y is pi over 6 when x is 0, solve the differential equation dy by dx equals e to the x cosec 2y cosec of y. Once again, separate the variables is the aim of the game. So dy by dx as it stands, that's no use to us. That is no need for that to be a denominator anymore. So first step, let's multiply both sides by dx. That'll then give us on the left just simply dy, and on the right we're going to have e to the x cosec of 2y cosec of y dx. So all of the x stuff is together on one side, that's great, but there's also some y stuff in the way. All the y stuff needs to live together. So I want all of this to disappear and live over here somehow. So I'm going to divide now both sides by cosec 2y cosec y. So I'm just explaining what I'm doing. What the earth am I writing here? Cosec y, I mean to say. And on the other, again, same thing. Divide by cosec 2y cosec y. So this side, I'm going to get dy, and that's going to be all divided by cosec 2y cosec y. That'll equal on the other side e to the x dx. Now I could just integrate both sides now, but what I want to consider is what's 1 over cosec? What's 1 over cosec? So we've got cosec twice, 1 over. Well, the third letter is s. Sine is 1 over cosec. Therefore, 1 over cosec goes back to sine. So I can write this better. This is the same as sine of 2y sine of y with respect to y. Over here, I can leave that as it is, just e to the x dx. Now, this looks much nicer to integrate. This is absolutely fine. So now just stick the integral symbol in and proceed. So, this side here, sine 2y, sine y. I'm going to rewrite sine of 2y using the double angle formula. So sine 2y, I'm just going to rewrite as 2 lots sine y cos y. So I've got 2 sine y cos y times another sine y with respect to y equals e to the x dx. All I've done there, just one little step, I've rewrote sine 2y as 2 sine y cos y using the double angle formula. Now what I can say, I'm going to put the 2 on the outside of the integral. Now I've got sine squared y. In fact, I'll put cos y first. So cos y sine squared of y dy. Now I'm just going to integrate this. E to the x integrated just integrates to itself, so that becomes e to the x plus c. On this side, this is essentially reverse chain rule. So over here, what I'm going to suggest we do is let u equal sine of y. So if I just write this in here, so I'm going to let u equal sine y. Therefore, if I differentiate u with respect to y, I get cos y. So therefore, du is the same as dy divided, dy I mean to say, get my head switched on. If I rearrange this, I should say that dy is du divided by cos y. So I'm going to use that here. So now I'm going to get 2 lots of the integral of cos y. Sine now is u, so I'm going to call that u squared. And dy is the same as du over cos y. So I'm going to write du over cos y. That equals e to the x plus c. Now I can cancel the cos y's off. So now I'm going to get 2 lots integral of u squared du equals e to the x plus c. Integrate u squared with respect to u. That's going to give me 1/3 u cubed. Will equal e to the x plus c. Just going to remember what u cubed actually was. Give myself a bit more space down here. So u was, of course, we call that sine of y. So if we put this back in now, what I can say now is I've got 2/3 sine of y cubed, which we write sine cubed of y, equals e to the x plus c. Now this one does have boundary conditions. So now I sub in, we said when x was 0, y is pi over 6. So we sub in the boundary conditions now. So then what we're going to get is 2/3 sine cubed of pi over 6 equals e to the 0 plus c, just by subbing in that y is pi over 6 and x now we're picking to be 0. So let's just fill in the details. So I've got 2/3 sine of pi over 6. Well, if you try that, you should find sine of pi over 6 is a half. It's the same as sine of 30 degrees in normal degrees. So if I take a half and cube it, half multiplied by a half multiplied by a half is going to be 1/8. So 2/3 of 1/8. E to the 0, of course, is just 1, then plus c. So 2 times 1 is 2, 3 times 8 is 24. 2 over 24, that's the same as 1/12. So 1/12 equals 1 plus c. Therefore, c will be 1/12 minus 1, which is minus 11 over 12. So now we have that condition. We know that c is 11 over 12, minus 11 over 12, sorry, I mean to say. We have our solution. So therefore, 2/3 of sine cubed y, that must equal e to the x plus c plus minus 11 over 2 is same as just minus 11, so I mean 11 over 12. We get that. So the final solution, 2/3 sine cubed y, is e to the x minus 11/12. Let's now have a look at the final one. Work at example 4. So parts A, B and C, this was an old exam question, 12 marks. So first of all, what it says, you need to express 2x minus 1 all over x minus 1, 2x minus 3 as partial fractions. So if I just do maybe part A here in a little square, so I'm not going to get in the way of anything else, just do part A here. So the first part is going to help us with part A and the first part, sorry, is going to help us with B and C. So let's just set 2x minus 1 all over x minus 1, 2x minus 3 equal to some constant A to be found all over x minus 1 plus some constant B to be found all over 2x minus 3. If we now multiply both sides of this by x minus 1 and 2x minus 3, we get that 2x minus 1 must equal A brackets 2x minus 3. Because if I were to multiply this fraction by all of this on the denominator, the x minus 1 here would cancel the x minus 1 and multiplying it by, just leaving us with the 2x minus 3. In the same way here for the b term, I'm going to get b lots of x minus 1. I can now substitute in different values of x to evaluate each one of these constants a and b. So first of all, I want one of these brackets to vanish. So I'm going to pick let x be equal to 1 first, so this bracket here becomes 0. So if x were equal to 1, 2 times 1 minus 1 becomes 1. Then we get a brackets 2 times 1 is 2, minus 3 is minus 1. So 1 equals minus a, therefore a equals negative 1. Next I'm going to pick when x is equal to 1.5, because then this a term will vanish. So if I let x equal 1.5, 3 over 2 or 1.5, whichever way you prefer to think of it, 2 times 1.5 is 3, minus 1 gives 2. The a bracket vanishes, then I get b multiplied by 1.5 minus 1, which is 0.5. So 2 is half of b, therefore b itself, of course, has to equal 4. Therefore, we have our answer to part A. So we just need to conclude and say, therefore, 2x minus 1 all over x minus 1 brackets 2x minus 3 that must equal a, which is minus 1, all over x minus 1, plus b, which we've worked out is 4, all over 2x minus 3. So that part A will be useful to us later on. So next we have part B. So part B, it's now asking us to, given that x is 2 or greater, find the general solution to this. So what I'm going to do first of all, I'm going to suggest, like I suggested before, the denominator of the derivative notation has no business anymore being a denominator, so I'm going to multiply both sides by dx as the first move. What I now have, I'm going to have 2x minus 3 brackets x minus 1 multiplied by dy. That'll equal 2x minus 1 on the other side multiplied by y, now multiplied by dx. The aim, of course, is to have everything to do with y on this side, everything to do with x over here. So I've got a y here which I don't want. I want x stuff on this side, y stuff over there. So next I'm going to divide both sides by y, which will then give 2x minus 3 x minus 1 all over y dy equals 2x minus 1 dx. So I'm making progress, but I still have x terms over here. So I need to divide by 2x minus 3 and x minus 1. On both sides. So that will now give me just 1 over y dy equals, and I've got 2x minus 1 on the top, and dividing by 2x minus 3, x minus 1. I'm going to write it as x minus 1, 2x minus 3 though. So now you can see how, hopefully you can see, how part A is going to help us in just a moment. dx. I can now, I've got everything in terms of y on this side, everything to do with x over here. I can now choose to integrate both sides. But what I'm best doing first is using part A. So at this stage, use part A to simplify this into something I can then integrate. So if I use part A for that, I'm now going to see that 1 over y dy, that will become ln mod y. Over here, I'm going to be integrating this instead, because this form here is the same as that. So I'm just going to switch that around and replace it with that, because that can be integrated in terms of natural logarithms. So I'm going to get now minus 1 over x minus 1 plus 4 all over 2x minus 3 with respect to dx. So now we can just proceed and integrate. So this side, I've got ln of mod y. Now this thing, if I integrate this, the derivative of x is 1. On the top, I've got negative 1. So that's minus 1 multiplied by the derivative of the bottom. So if I integrate this, I'll get minus ln mod of x minus 1. Over here, the derivative of 2x minus 3 is 2. The top, the numerator, is double of that. So this will integrate to double 2 lots of 2x minus 3. And now I need a constant of integration. But to keep it consistent in terms of what I have here, instead of writing c for the constant of integration, I'm going to choose to do my constant as ln of k. Because by doing it this way, I can combine all of this into a single logarithm, which is what I'm going to do now as the next step. So next, I've got ln mod y over there, and over here, I can combine using the laws of logs. Log of one thing plus log of the other, I can combine these into a single logarithm. So I've got ln. By the way, as well, because that's 2 lots of 2x minus 3, I can combine that into a power. So I can imagine this as becoming a power in a moment. So I've got ln of 2x minus 3 squared times k. In fact, I should put the k first, because it just makes it easy. So k times that, what I wrote down squared, is k, then 2x minus 3 all squared, all over this x minus 1. Because again, log of one thing minus log of another is the same as log of one thing divided by the other. If this is unfamiliar, just need to revise your laws of logs slightly. So ln mod y equals ln mod of all of this. That can only be the case if y equals k brackets 2x minus 3 all squared all over x minus 1. So therefore, the general solution is y equals some constant k multiplied by 2x minus 3 all squared all over x minus 1. For c, we now need to find the particular solution. So we need the boundary conditions. So now I'm going to do is sub in y is 10 when x is 2. So y is 10 and x equals 2 into the above. So y, 10, equals k. 2x becomes 4, minus 3 is 1, so k brackets 1 all squared, all over 2 minus 1, which of course is 1. So therefore, k only have to equal 10, because 10 equals k times 1 divided by 1, k equals 10. I've just noticed this 2 is annoying me. Apologies if it's not annoying you, it just looks very, very ugh. So I'm going to make it look like a clearer 2. There we go. So because k is 10, we've got the actual particular solution. So y equals 10 lots of 2x minus 3 all squared, all divided by x minus 1. And that finishes off worked example 4. So I hope you found those examples useful, but the most use you'll find is by doing the questions yourself. So on that note, if you get your blue book out, I'm going to ask you to turn to page 325 and 326, exercise 11J. I would suggest to try all the exam type questions and the ones with a P next to them. That's questions 4 through to question 12 inclusive, then question 14 and question 15. The more you practice, the better you'll become. Thank you very much again for listening. Best of luck with the practice, and let me know if you're struggling in the comments or in person. So from Mr. Bailey, take care of yourselves and hope to see you all very soon.